Nice introduction. I think you covered all the highlights for sure. So today I'm going to talk to you about Zika and a few things that we've been doing since the initial stages of the Zika invasion of the Americas. I think this talk is actually going to be sort of more fun to give than it was before because we've sort of followed up with so many different sort of applications by now that, yeah, I'm looking forward to telling you about this. So I think everyone in this room and at Riverside and elsewhere is very familiar with Zika, but I'll just quickly go through some background to sort of highlight sort of how I came about to work on this and to do the type of work that I've been doing. So Zika, of course, is transmitted primarily by Aedes aegypti mosquitoes. It's a viral disease. It's been around for a while, obviously, going back to around 1950 or so, where we've seen sort of sporadic outbreaks, but never anything of the scale that we have seen over the last few years in the Americas, starting in Brazil around 2014 and then spreading to numerous countries throughout the Americas and elsewhere in the world as well. But of course, this really got everyone's attention in early 2016 when the link between Zika virus infection and microcephaly was established. And shortly thereafter, the World Health Organization took a relatively rare step of declaring this a public health emergency of international concern. So I and many others have been following this, of course, in the months preceding this, but really at that point, it really caught everyone's attention. One thing that particularly caught my attention, and this is just one source, but others sort of made similar statements around this time, just within days of this public health emergency being declared. This is just one example from an editorial in Nature, where you notice the part that I've highlighted, that researchers must work fast to assess the extent of the threat. So the reason I want to draw attention to this is because when that association was made between Zika virus infection and microcephaly, obviously at an individual level, that's a really bad outcome. That's something that's very worrisome. So the natural next question is, how many people could be infected by this? Obviously, based on the epidemiology of dengue and the distribution of Aedes aegypti, it stood to reason that a lot of people could be impacted by this, which is why there was so much concern. But really, there was clearly a need to try to put some numbers on this and actually come to some more quantitative projections of how many people might be at risk of this condition. So thinking through sort of the natural sort of questions that a modeler might ask him or herself during an early stage of an epidemic like this, I just sort of want to walk you through some of the factors that went into this and some of the particular aspects that are somewhat unique to Zika and somewhat challenging. So one thing that's challenging about making projections of how large this epidemic could be, one thing is data availability. So if we look at this graph on the top right, you see this is an example from the Ebola virus epidemic in West Africa, where after a number of weeks, case reports were counted up, and basically different types of models were used to sort of extrapolate some curve of how large the epidemic would grow from there. So this is sort of a traditional approach. There's obviously a lot of different ways to go about this, but generally, the one drawback of this is that you wait over some period of time for data to accumulate, you fit a model to it, and then you make a projection. Whereas very early on in the Zika epidemic, I think data was very scarce, and we really hadn't rounded up and sort of made a picture of what was going on. So this was one challenge of sort of waiting long enough to get that picture from the data. Another question is data interpretation. So here I've listed just a few challenges that were faced at that time, and that I think are still challenges. One is that there are a lot of asymptomatic infections or very mild infections that aren't going to show up in passive surveillance. There were, and I would say still are, a lot of limitations in diagnostic capabilities, especially on a broad scale to inform public health surveillance. There's a lot of variability in reporting within countries, across countries, over time. We just can't put a sort of single expansion factor on how many cases are and how many infections that translates to. And there's been a lot of misdiagnosis with other arboviral infections that have been co-circulating, and at this point that's actually been documented quite well, and it looks like it's been quite a big issue. So given all these numerous limitations that sort of challenge some of the typical approaches that modelers would take to projecting how large this epidemic would be, there are a number of sort of ways that you could proceed in this situation. One, we could just sort of wait until all these issues are resolved before we apply our methods. We sort of feel that all our assumptions are good, the data quality is good at that point. But then that raises the question of, can all these issues ever be resolved? How long is that going to happen? And by the time all these issues are addressed, is it going to be too late to contribute anything? Will we already have observed the epidemic and not really need a projection of how large it's going to be? So one very early effort to try to get a handle on the population at risk involved basically sort of an ecological niche modeling approach, or species distribution modeling approach. So the idea here is to basically look at all the different places in the world that Zika has ever occurred before. Maybe I'll stand back a little bit. And then to
sorry to interrupt, but we've lost Sam.
It's on
okay,
mute.
I don't think I touched it.
No. Yours? Is that better?
Yep.
Perfect. I don't know. It was on mute.
Okay. All right, so in any case, if you look at this map, the red areas, that's where a model like this would predict a very high probability that Zika could occur there. The more gray colors, that's very low probability. So when you look across all these different areas and you look at all the places where Zika looks like it could occur, and you add up the total population in those areas, this one study found a number of 2.17 billion people that are in this way at risk of Zika virus infection. The issue that I have, I think this is nice, and this probably does capture a lot of the spatial pattern and risk. But for me, I find this very difficult to interpret. What does that 2.17 million or billion number really mean? Is this people who really stand a risk of getting infected? Probably not. So how do we sort of interpret that number? Do we actually use a number like this to guide vaccine producers about how many doses they might, what the market might be for a vaccine, for example? So how do we actually sort of use a number like this? So at the time I saw this, and I was trying to think about sort of how we could come up with maybe a better approach, a more refined approach. And I actually thought back to a graduate course that I taught the previous semester on population biology of infectious disease. And one of the sort of key sort of classic epidemiological concepts that I thought back to was the behavior of an SIR, or susceptible infected recovered type model, where it could be a situation similar to Zika, where you start out with a highly susceptible population, like you see with that blue curve on the right. You have an epidemic occur, that's the red curve, so it shoots up after a while, but then it becomes self-limiting at some point because the infected people sort of run out of steam, and the epidemic sort of burns itself out due to herd immunity. And so what you notice there on the right is with those brackets, it shows the proportion of the population that becomes infected over the course of the epidemic. So I'll refer to this as the infection attack rate. And then the proportion that doesn't become infected, that's some population that's protected by herd immunity. So one really sort of neat classic insight from models of this sort of phenomenon is that there should be a one-to-one relationship between the basic reproduction number, R naught, which is a measure of transmission intensity, and how much of that population ends up getting infected over the course of an epidemic. So basically the approach that we thought to take was, if we can use environmental variables and whatever other information we can come up with to try to quantify what that basic reproduction number is, which is something that a lot of people have done in mosquito-borne disease modeling, can we sort of translate that into an estimate of what the infection attack rate might be in different locations with different environmental conditions? Okay, so to do that, we started off with this really basic formula that probably many of you have seen. Here we're making the basic reproduction number R naught a function of temperature, so that big T. There's a number of different places where temperature and other environmental variables could enter into this and affect different parameters relevant to mosquito-borne disease transmission. So a couple that we looked at were for temperature. Just go ahead and highlight that. We looked at the effect of temperature on adult mosquito mortality and also the incubation period of the virus within the mosquito. So those are two very important ways that temperature affects transmission. In addition to that, we also looked at this really nice Aedes aegypti occurrence probability projection that Moritz Kramer and colleagues came up with. So here we have something similar to that sort of Zika environmental risk that I showed you earlier, but here, what's the probability that Aedes aegypti are present in different locations? So this isn't quite a measure of mosquito density, but we sort of took it as a relative measure of density, or sort of a proxy for that. And so we incorporated it into R naught that way. And then the final thing that we wanted to account for, to some extent, is to account for the fact that even if you have an area where there are lots of mosquitoes present, if they're not coming into contact with people and engaging in blood feeding on humans, then they're not going to be so relevant to transmission. And so we expected that in a sort of poorer area, sort of less socioeconomic means and so forth, that you'd have sort of greater contact potentially between people and mosquitoes, whereas in a wealthier area, even if the mosquitoes are present, there might be less contact between them, so that could affect R0 as well. This is something that's very hard to quantify, it's very complicated, but we at least wanted to try to make an attempt to account for this to the extent that we could. And so we took into account this GECON economic index, which is basically a per capita purchasing power, or sort of per capita GDP that's been mapped at a relatively high resolution spatially across the globe. All right, so once we took all those different factors into account, for any given 5 by 5 kilometer grid cell in Latin America and the Caribbean, we quantified this. And then on the x-axis on this graph that you see, that's our quantification for a number of different locations, what that basic reproduction number is. We looked at all the relative, sort of relevant epidemics that we could to try to calibrate the relationship between the basic reproduction number and an infection attack rate. So you'll see that these are mostly chikungunya epidemics from different places where before the epidemic occurred, this was presumably an immunologically naive population. And there was a serological study done after the epidemic to estimate how many people it infected. So that's what you see here, and you see their values ranging from almost 0% of the population to as much as 75% of the population that got infected in these different epidemics. So we really had quite a spectrum of variation to try to match. So you see this curve, this black curve that sort of follows those dots somewhat. That's basically our fitted relationship between this basic reproduction number and the infection attack rate. So obviously, there's a lot of residual variation around that we don't quite pick up on, but nonetheless, for areas that tend to have high infection attack rates, we tend to capture that, and for areas that tend to have very low infection attack rates, we tend to capture that as well. So at least as sort of a very beginning of the epidemic, just trying to come up with some rough numbers, we thought this was a pretty decent approximation. All right, so taking that curve and all these different environmental variables that go into that, if we just apply that process across this entire area, we come up with a map on the left. So this is our projection for the infection attack rate for each grid cell on this map. There's a lot of different caveats to this, of course. One thing I mentioned, but I'm not going to show explicitly, is that we try to account for uncertainty in lots of different parameters that were involved in this. So there is a lot of uncertainty around these projections. I'm just showing you the median here, since that's easy to look at. Another thing is that these projections are really conditional on an epidemic occurring in one of these places in the first place. So we're not accounting for processes of spatiotemporal spread, the probability of introduction, and things like that. This is really just if there's an epidemic in these locations, this is how large we would expect it to be. But what we did to actually put this in terms of numbers of people is we combine these projections of infection attack rate with very high resolution projections of where people live, how many people live there, and also what birth rates are in different areas, since we were interested in quantifying not only the general population at risk of Zika infection, but in particular the population of pregnant women at risk of Zika infection in a given year. And I think it's really important to sort of combine these two, because you see things like it's very dark in the Amazon region. We project a high infection attack rate there based on all these environmental conditions, but clearly, very few people live there, so that's going to contribute relatively little to how many people we think would be infected across the region. So I think there's a lot of value in doing something very spatially granular like this, because you can sort of appropriately line up people and risk in a very detailed way, whereas if we were averaging over a state or a country or something like that, we'd really probably be washing away a lot of the really important variation in how risk lines up with populations. All right, so when we put all these numbers together and we add them across this region as a whole, we come up with a total of 93 million infections that we would project sort of as a point estimate, give or take several million, of course. And in terms of childbearing women, this is women that are not only pregnant, but would actually come to full-term birth. This would add up to 1.6 million infections. Obviously, it's very important to keep in mind that this is infections, not cases. So the number of reported cases would be far lower in both categories. Another thing to keep in mind is what I said earlier about the fact that all of this is conditional on an epidemic occurring somewhere in the first place. A lot of these places we would expect maybe the virus just never reaches for whatever reason, or maybe an epidemic might start but then sort of fade out due to stochastic reasons or something. So we kind of view these numbers as upper limits, but nonetheless, we think fairly reasonable upper limits. If you look at a study of dengue and estimates in this region from Samir Bhatt et al., they estimated around 54 million dengue infections in this region per year. So if we think of this number as sort of over the course of the entire first wave of the Zika epidemic, which maybe would take a couple of years or so, these numbers I think are sort of a reasonable order of magnitude at least. So in any case, this is kind of the initial work that we did, just sort of coming up with these numbers in total. And of course, the media was very interested in this, in particular the number of pregnant women who might be affected. And they really latched on to this 1.65 million number you can see from some of the headlines here. They also really pressed me to sort of come up with a number of how many women would actually have microcephaly. I said, well, that's very difficult for all sorts of reasons. We're still trying to figure that out. So in any case, this was a really good crash course for me in terms of dealing with the media and trying to sort of relay things in a careful way. But I think overall it came out pretty well, and there weren't too many unreasonable things that got out there. But it did really take a lot of communication and sort of working with these people to get the story right. All right, so that was sort of the initial splashy story. But now what I want to talk to you about is like how we're actually using these things in ways that I think are much more practical and applied, and more important than coming up with a single big number that grabs headlines. So the three applications I'm going to walk you through. First, how can we actually relate this to what's going on in the US? Obviously, we know that in the US we didn't have some epidemic of millions of infections. So how can we still maybe apply these numbers somewhat to come up with an assessment of risk that's realistic for the US? And then I'm going to talk to you, the second and third points are somewhat related, where we can use these projections to come up with information that's of value for planning for vaccine trials in particular. And so I'll get into that more later. So first of all, let's focus on the US. So before I get into this in too much detail, I just want to highlight that I'm just a lowly middle author on this work. This is really spearheaded by Spencer Fox, who is a PhD student at the University of Texas at Austin. So this is a dissertation chapter of his. It uses the projections I just told you about, so luckily I had an opportunity to be involved, but really all the credit goes to him. But I think it's a really nice demonstration of how this type of information can be applied. All right, so starting off, again, if we just take these, any number of sort of ecological or environmentally based models to assess risk, any one of them is going to find that, we have mosquitoes that are capable of transmitting Zika. We have temperatures in many areas that are conducive to that. So, it would be easy to make a prediction, a reasonable prediction with a reasonable model. You have lots of Zika virus transmission in the US. However, of course, we did not see that. So that raises a lot of questions about what these models are getting wrong and how we can actually make more realistic projections. So here's just one paper that I'll just sort of reference to sort of support this idea that you can come up with really big projections. So this paper by Carlson et al., they took several different environmental niche type models of Zika risk. They put them into a transmission model for Zika, and they came up with epidemic curves like this, which if you look at the y-axis, goes up to millions of people. And all the different flavors of models they ran, they came up with no fewer than 12 million Zika infections in the US. So clearly that's not what happens. And so that raises a lot of questions about how we can sort of improve the modeling to come up with more realistic projections. A lot of you might be familiar with a number of different papers that have looked at these differences. I think these are really fascinating studies. This is one example from Paul Ryder, where he and colleagues did some work on the Texas-Mexico border, where they looked at border communities that were very similar in many ways, environmental conditions very similar, obviously temperature. On the Texas side, in this case, they even had a higher abundance of mosquitoes than on the Mexico side. Yet for dengue, you see much higher levels of seroprevalence to dengue in that population on the Mexico side than you do on the Texas side. There's all sorts of potentially complicated factors that could be explaining that, but nonetheless, anytime the studies have looked at this, they've seen really stark differences just right across the border that are due to factors that are really kind of hard to capture in models. All right, so the approach that we wanted to take with this, I think was a really nice one that Spencer came up with. So the idea was to take these projections from our model, which is again based largely on environmental conditions and things like that, and use that as our starting point. Okay, this is our sort of our prior belief in a Bayesian sense of what we think the risk is in different areas. But over the course of the epidemic, let's actually watch what happens and take into account that data through a process of data assimilation to update our prior understanding and actually sort of learn that and come away with sort of improved understanding of what risk is by seeing what goes on during the epidemic. So just conceptually, the idea here is that let's say we have these green dots represent imported cases of Zika into the US, and we're going to be focusing on Texas in particular. So if we have some number of importations, if we have some estimate of local risk, that's going to lead us to some expectation of observing sort of short chains of transmission like the ones you see here. So here we see several different locally acquired cases in red that we would expect to pop up given a certain number of importations and a given amount of risk locally. But so that's our prior assumption. But what happens is that we observe importations that aren't leading to any subsequent transmission, or maybe they lead to a little bit of subsequent transmission. But in this case, let's say we just have an isolated imported case. What we're going to do is we're going to update that prior belief and sort of downweight it. We're going to sort of say, well, here we have an observed piece of data. It didn't result in a big outbreak, so we're going to sort of lower our estimate. And every week that we go by and we see things like this happening, we're going to sort of continue to lower our estimates. On the other hand, if we see an outbreak happen, we'll sort of maybe readjust it sort of upwards a little bit. So before I show you the real application of this to a real data set, I just want to show you sort of a hypothetical that we use to sort of work this out and sort of as a proof of principle. So again, this study was focused on Texas. And if you look at the August 2016 map, this is a projection of the basic reproduction number for Zika that comes from the projections that I showed you earlier here for the month of August. And you see in some parts of Texas, based on that and based on these variables, we would expect for the reproduction number to be above 1 in a number of places. To an extent that you would expect a good amount of local transmission. But if we allow for, I believe, 15 importations, terminal importations, that's referring to importations that don't result in any local transmission. What you see is that if that happens 15 times, we would sort of scale down our estimate of R naught across the map to the extent that what you see on the right. So there we take these R naught estimates that are above 1 in many cases, and we scale them down to where they're sort of never getting above, like, let's say 0.5 or something. So just as a hypothetical, this is what we would see if there were 15 terminal importations. All right, so this is what we actually see. It's a little more complicated, but I think this graph really shows some really nice information. So if we start at the very top, this parameter on the x-axis, this scaling factor, that's sort of how much we're going to take that map of R naught and sort of weight it up or down relative to the prior assumption. So we start off with sort of no understanding really of how we're going to weight that, how we're going to scale it. So it could be anywhere between 0 or 1 in terms of what the risk is. But as you see, each of these sort of, starting from the top and going down, each of these little density plots is a sort of updated estimate of what that scaling factor should be. So over the course of the first several months, you see that it doesn't really change a lot, despite there being a number of importations. And the reason for that is that during those parts of the year, the model actually projects that there's pretty low risk of local transmission. So seeing importations that are terminal actually isn't inconsistent with the model's projections in the first place. But once we start getting into the warmer season and you see those shapes being colored in darker red, you start to see that distribution sort of shift towards the left, where we're saying, well, now we're at a time of year where there's actually a pretty good amount of risk, but we're not seeing a whole lot of local transmission. So let's sort of downweight our estimates of what risk is. And so you see that distribution sort of collapsing down towards the left. But then the two blue triangles show two instances where there was not only an importation, but also a locally transmitted case that was associated with that. And there you see that bumps up the estimate a little bit relative to what it was from the case where we were just seeing the importations that didn't result in any local transmission. So in general, this is kind of how our understanding of the situation sort of evolved over the course of the epidemic in Texas, based on the patterns of importations and local transmission seen there. So again, just to sort of recap our prior understanding across different months, from top left to bottom right, this shows sort of a monthly set of values, a median projection, and then the 99th percentile. So this is the most extreme projection of risk that we might come up with. So this is our prior understanding. And again, you see in the summer months, there's a lot of potential for transmission that this set of projections is coming up with. But then after we take into account by the end of the year, all those importations that did not result in local transmission, we see that lowers our estimates of risk considerably, where again, only in a couple of months in the most sort of extreme sort of tails of the distribution, we expect there to be a really considerable amount of transmission based on our updated estimates. All right, so the one sort of final piece of this that I thought was really nice was in 2016, that was sort of treated as a training period where each of these black lines shows the number of importations, I believe on a daily basis in this case, that came into Texas. So you see lots and lots of importations happening. These results got downweighted. And then what we did is we looked at 2017 as a testing period where we said, okay, we've learned sort of what the risk is from 2016. Can we then go and apply that in 2017 to say, given a certain number of importations, how many local cases would we expect? And as you see on the right, the importations had slowed down somewhat in 2017, but there were still a pretty good number of them. And there was one local case that was identified. And basically, if we look at the projections, given that number of imported infections and how many local cases we saw, really the projection was pretty spot on with what we observed. So there was one locally observed case, so that's shown with that line in blue, and that's really about on average what the model predicted after all that updating had occurred. So if we hadn't had that process of updating our projections of risk, we probably would have anticipated a much larger number of local cases in 2017, but after taking this into account, it seemed like it sort of got risk right in a sort of relative sense. So, all right, so moving on to the second application of these projections. The question is for vaccine efficacy. At one time, there were as many as 47 different vaccines for Zika that were under development at various stages, with 12 of them progressing towards clinical testing. That number has actually come down somewhat because I think a lot of manufacturers have been discouraged about the prospect of doing trials just like this. But in any case, there has been a lot of interest in developing Zika vaccines. But a really important part of that, obviously, is not only to develop the vaccine, but to show that it's efficacious, that it's actually going to lead to protection with respect to some clinical endpoint, primarily just prevention of Zika virus disease. And in order to do that, though, any trial is going to have people who are exposed to Zika virus in the first place who might actually be protected, or a signal of that can be detected. All right, so in terms of where to set up a Zika vaccine trial, the question is, sort of what makes a good candidate for a trial? Well, we need to have a place with a high infection attack rate. The more people that are going to get infected, the easier it's going to be to pick up on a signal of the vaccine actually working effectively. And so the trick is to identify locations, not just with a sort of high risk in the first place, but given that we're already through the epidemic to a good extent, which places are still at risk. So which places sort of have a high risk in the first place, but have not yet experienced a big epidemic. If we just went to and set up a trial in a place that had a lot of Zika cases, it very well might be the case that place has sort of already burned itself out. There's enough herd immunity that it's not going to have future transmission. So this is really the sort of careful balance of future risk versus sort of past incidents that we're trying to evaluate. So to illustrate that, we looked at it earlier on at sort of island-wide projections for Puerto Rico. And our models come up with an estimate of around 25 to 30% of the population that we thought might be infected with Zika in that area. So that's good for vaccine trial site selection in the sense that there's a sort of high risk in the first place. But we talked with Michael Johansson at the CDC in Puerto Rico, and he'd sort of done some back-the-envelope type of calculations with the clinical incidence data that they'd gotten there. And he actually independently came up with a pretty similar estimate to what our projection was. He thought that around 25 to 30% of the population had probably been infected at that point. So what that means is that our sort of initial projection of risk, probably all the people that would have been infected in the first place probably already have been by now. So that's actually going to make this probably not such a great place to carry out a Zika vaccine trial. So we want to look for a place that sort of has a lot of risk, but where that risk hasn't sort of materialized into infections yet. All right, so I showed you in the first part of my talk how we come up with our initial projection of what the risk is in the first place. So the second really tricky part is to estimate how many people have been infected so far. Now we have passive surveillance data that we can use to guide this, but like I mentioned earlier on, it's really sort of difficult to interpret and translate that into an estimate of how many people have actually been infected. So nonetheless, that's what we're trying to do here. So what we do is we take advantage of the fact that there's several different types of cases. There's confirmed, suspected, Guillain-Barré, microcephaly, and in some cases even more direct estimates of infection, like through seroprevalence estimates or blood bank data. So I won't go through all the details, but in general, what we're trying to do is estimate this script I here in the middle, which is the proportion that we think have actually been infected based on how many are actually showing up in these different categories through surveillance data. So we did this in Puerto Rico, where we really have all of these different data types at the sub-island level and across 70-some different municipalities. But this becomes a lot more challenging in other countries where the data are a lot more incomplete. So I'm going to show you just one quick example in Mexico, where they've reported state-level cumulative confirmed cases, but we don't know anything about suspected cases. We only know Guillain-Barré and microcephaly at the national level, but not subnationally. So it makes it somewhat more difficult to pick out which portions of the country might be at the greatest risk. And these parameters down here at the bottom, that's what these symbols are at the bottom. What we do is we take our posterior estimates of what these parameters are from Puerto Rico, from our analysis there, and we use those as prior estimates of what those parameters might be in Mexico or other countries that we're looking at. So when we do that, at the national level, you see we come up with an estimate of what the infection attack rate was that's really quite low, but when we look subnationally in different states, we see a much wider variation. That's these shapes on the graph on the bottom, where we estimate that infection attack rates across different states have ranged all the way from low single digits up to 30+%. So what we want to do is see which of these places where we've experienced a big epidemic line up with the places where we project there to be a relatively large epidemic. All right, so these graphs are a little bit complicated, but I think they kind of show what we're getting at and sort of how these projections work. So on the left-hand side, this is a projection of the population that is remaining at risk of future Zika virus infection as of November 28, 2015. So, really sort of before the epidemic started, this is what we would project. Different states are shown by different rows, and these different shapes show a sort of probabilistic estimate of how many people we think might still be at risk of Zika virus infection in these different states. So you can imagine if you're planning a vaccine trial at this point, if you're following our recommendations and you actually believe what we're saying, you would go to Sinaloa and Nuevo Leon and several of these other states that are sort of the top of our list. That would give you the best chance of getting people in your trial who had actually been infected by Zika. By the time January 7, 2017 rolls around, you see on the right-hand side, this is our sort of updated estimate of what the population at risk is. So what we've done is we took our initial projections, and basically if there was a large epidemic that we estimated to have occurred in some of these states, that would sort of take those distributions and drag them towards the left, because we're sort of removing people that we think were initially at risk, but they've already been infected, so they're not going to be at risk of a subsequent infection. And I think it's kind of interesting. We're still in the process of sort of formally quantifying how well these predictions hold up. But if you look at the sort of top 10, like 3 through 7 in our ranking roughly, you see that a lot of those distributions did sort of move from right to left. So that indicated that a lot of places near the sort of top of our list did in fact experience a pretty large epidemic in that sort of initial phase in 2016. All right, so what happens if we make a sort of subsequent prediction for 2017? There we see that there's sort of less activity in general in terms of Zika infections. So you see less movement of those distributions from right to left. But again, if you kind of squint and you sort of study this, you see that some of the places like our second ranked state, that one actually we estimate to have had an attack rate during this time period of, let's say, 5 to 6% in terms of infection. So that actually could have potentially been enough to inform a vaccine trial if enrollment was sufficient. So this is still ongoing work. Actually, Chris and a number of others are involved in this. And this really constitutes the collaboration between my group at Notre Dame and collaborators like Chris, but also Justin Lessler, Johns Hopkins, and Alex Espignani at Northeastern University. Mark Fisher at the CDC has sort of approached all three of us to sort of make projections with very different approaches of a similar nature. And we're sort of trying to get together and see where our projections line up and where there's consensus among the models that, yes, these are the places that where it would be a good idea to do a Zika vaccine trial. To some extent, this is actually informing some people who are planning Zika vaccine trials, but it's sort of the first time that something like this has really been done. So we're still sort of figuring out a lot of this. But there is a bioRxiv preprint that I've shown here that lists what we've done on this work to date. All right, so quickly, I just want to mention a sort of third application. This is even more recent work where we have a similar goal of projecting which places might be at a certain level of risk of infection during an epidemic. But here we're in the more challenging context. We're actually going to talk about chikungunya because that's one where, you know, that sort of large epidemic wave in the Americas has come and gone. But there's still sort of sporadic chikungunya epidemics across the globe, throughout Asia, Africa, and other places. And so the question is, if an epidemic pops up in one of those places, we see some transmission activity, how big might that epidemic get, and would it be large enough potentially to support a vaccine trial in a given time frame? All right, so this is a little more complicated though. We're not in the context of an ongoing epidemic, so there's less likely to be transmission in the first place. And if we do detect some cases, to roll out a vaccine trial, that would have to happen pretty quickly. So that's one challenge right off the bat. Also, inferring population immunity in this sort of situation gets a lot more complicated, especially in places like Asia and Africa, where there's been chikungunya or Zika transmission for many decades and sort of sporadic outbreaks. It's just much more complicated in terms of what the immune profile of the population is. And we don't have the luxury of passive surveillance data like we used in the Zika epidemic to actually infer how large the epidemic was in different areas, just because it's been so long and so much has been going on over the course of decades. So we really have to rely on serological data, but that can also be complicated to interpret for a variety of reasons, some of which include cross-reactivity with other pathogens and things like that. All right, so the question is, who would actually be crazy enough to try to sort of make some sense out of a situation like this? The answer is DARPA. So a pretty good amount of the funding for my lab comes from DARPA. They've awarded me a Young Faculty Award specifically to do chikungunya forecasting. They had a chikungunya forecasting challenge a few years ago, and I sort of had some ideas about ways that we could sort of improve on that and make that a more productive effort. And so they've been of interest in this, and this really fits in within a sort of broader paradigm of theirs of wanting to recognize an epidemic very early on, like Zika, chikungunya, many others, and to be able to very rapidly develop countermeasures over the course of that. And actually doing this forecasting and making projections that can inform trial planning is one important component of that, as are many other efforts. So one sort of very recent epidemic that's caught our attention in the context of chikungunya is in coastal Kenya. So at the very beginning of the year, there started being some reports of some cases there. It's still sort of difficult to figure out exactly what's going on. The surveillance data are very sort of spotty and very kind of difficult to get a handle on, but nonetheless, there's transmission activity there. So we're trying to get a sense of how large of an epidemic might be possible in that setting, given the immunological profile of that population and given our projections of what risk might be. All right, so basically what we've done is we've taken these same Zika projections and applied them in this setting. And you may think, well, Zika and chikungunya, they're not the same. That's of course true, and there's probably some limitations associated with that. But I'll remind you that a lot of our, the calibration of this method was actually done towards chikungunya seroprevalence estimates in the first place. So if anything, it might be a better model for chikungunya than it was for Zika. And one of the seroprevalence estimates actually came from up the coast in Kenya, just not too far from here. So we think this is a pretty reasonable projection of how large an epidemic could be, but in a naive population. So now the sort of thing we want to account for is, how does immunity affect epidemic size in a place like this? All right, so to do that, we just have to be very lucky when we started looking into coastal Kenya and try to get a sense of this. Desiree Lebeau down the road at Stanford recently published some serological work in a very similar area there, just sort of on that map that I showed you on the last slide. She looked at almost 2,000 different individuals across different ages from 2 different villages, looked at a couple of different serological assays for chikungunya exposure. There's a lot of cross-reactivity between chikungunya and on young virus, which has also been quite prevalent in this area. So basically what we did is we sort of used the information from her study to sort of put some brackets on what the range of population immunity might be in this population. So just to kind of quickly walk you through how we did that, because I think this highlights a really important point about interpreting serological data and translating it into an estimate of population immunity. So because transmission has probably been sort of sporadic over the years and affects different ages differently. We tried to go back in time based on different serological profiles of different people at different ages and estimate sort of when transmission was intense at different points in the past. So if you look at these sort of blue shapes up on the top right, if I can get my pointer. So starting in recent times, so 2005, 2009, this is an estimate of the force of infection. We go back to 5 years before that. Looks like it might have been a little bit bigger, but actually back here in the late 90s, based on the ages of people sort of beyond this age versus before this age, we see that there was probably a pretty large epidemic during that time, and so on and so forth for sort of similar patterns going back in time. But this is obviously a really important event that probably happened around that time period. And what that allows us to do is sort of reconstruct a picture in the past of what transmission was like. And then for a person at any given age, we can estimate what their sort of cumulative risk might have been over the course of their lives. And so that's what you see here. These black dots show the sort of empirical estimates of those different age groups. And this gray bar is sort of our reconstruction of that based on the blue curves up on the top. All right, so the really key thing is that we then say, all right, well, she happened to sample different people at different ages, which, you know, there are probably a lot of different considerations that went into the sampling, but it wasn't a completely representative sample of the population as a whole with respect to age. So what we did is we went and looked up what is the age distribution in this area, and then we applied these course of infection estimates over time to predict in different age groups what's the proportion of the population that's immune versus susceptible. And then we add across all age groups to come up with these estimates that you see on the right, which are population immunity projections on the whole. So depending on what we assume about the serology, that could be somewhere between 10 and 20% overall. All right, so these, you can still see this is a little bit of a work in progress, given that these aren't the prettiest graphs, but basically under different assumptions about immunity, combining that with our projections of risk based on those environmental factors, we get sort of a range of different estimates of what the population at risk of infection could be, given that there is an ongoing epidemic there. So starting at the right, so each of these rows is a different county, so we divided up this area into 3 different counties. The shape on the right, sorry, pointer. Okay, well anyway, the shapes on the right, that's under the assumption that there's no population immunity. So if this is just a virgin soil epidemic, we'd expect in these different counties for maybe as many as 40% or so of the population to be at risk of infection. But if we take sort of our lower estimate of population immunity of around 10%, we expect maybe the 20 to 30% of the population might be at risk. Whereas our sort of highest estimate of immunity of maybe around 20%, we'd expect that we could still support an epidemic potentially, but it would probably have an infection attack rate in the sort of low to mid single digits. So this doesn't quite pinpoint you know, how large of an epidemic we think there might be, but it really sort of combines all available information to give some sort of rough estimate. And I think this is still of value. So I looked just the other day, and turns out that they've been experiencing a lot of rain in this area, and there is still ongoing chikungunya transmission, and there's a lot of concern about increased epidemic activity of both chikungunya and cholera. So unfortunately, for the populations there, they might be at risk in the very short term, but potentially if a vaccine trial could be set up there in a timely fashion, it might be possible to get enough infections to actually inform an estimate of efficacy. All right, so in general, just to wrap up, what I've shown you is a pretty new and novel approach, I think, for projecting infection attack rates based on a variety of different highly spatially resolved different data sets, and also combining that with just sort of very classic and simple epidemiological theory. 3 different applications of this. We've applied this to try to get a better handle on risk in the US and shown that that is actually more consistent with what we saw in the Zika epidemic than other models that don't account for that information might have produced. And then the second and third applications have shown you some different ways that we can try to use these sort of baseline projections of risk and sort of discount them by estimates of epidemic activity to get a handle on what the remaining level of risk is and how feasible a vaccine trial might be in these different areas. So with that, I have a number of different collaborators to thank, including some that were supported by a National Science Foundation Zika Rapid Award that sort of sparked a lot of work on this area. also my lab at Notre Dame, and a number of different funding.